I guess we'll have a coffee break sometime soon, right? 45 minutes. Okay, now let me talk about RowHammer. I find this fascinating. And essentially, we're going to talk about these three in this order. And we're going to start with security, reliability, safety. And RowHammer is a very good example where security, reliability, and safety come together, in my opinion. So the high-level picture is this. Essentially, in today's DRAM chips, you can predictably induce bit flips in commodity DRAM chips that you can buy. And when we actually did the study for the first time, we found out that more than 80% of the chips that we've tested were vulnerable to these bit flips. And this is the first example that we could find actually, or that we were told also, of how a simple hardware failure mechanism can lead to a widespread system security vulnerability. It's the first connection between hardware reliability and system security in a widespread manner at least. And that's why people are writing these interesting articles that talk about RowHammer. So before I move on, I like talking about psychology also. One of my degrees is in psychology. Does anybody know who this is? There's a side channel clearly in this picture over here. So it's Abraham Maslow. He's a very famous American psychologist. He dedicated his life to understanding why human beings do the things they do, essentially. So you can see that he had a work in progress for his entire lifetime. And he's probably more famous for this than his face. And this is the hierarchy of needs that he developed, which is heavily used in economics, politics, psychology, social sciences, sociology. Basically, this says that humans need to have their basic needs satisfied before they can think about more sophisticated psychological needs, and before they can think about self-fulfillment needs. I think of this as you have to have shelter and food before you can worry about highest forms of abstract art, for example. Clearly, you don't worry about those if you don't have shelter and food and security. That's why security is so important. I think in computers also, we need to really start with reliability and security, because everything really is built on top of that. If you don't have a reliable and secure system, then who cares about its performance? Right? I'm going to deconstruct that later on as we go through this tutorial. I also use this picture in my lectures actually when I talk about security to freshmen. Does anybody know where this bridge is?
Tacoma something.
Yes, Tacoma Narrows Bridge. Have you crossed it?
No, I've seen the video.
You've seen the video? Okay, you've seen the video. Okay, so you know the story. Basically, this bridge doesn't exist. It was constructed in 1940, and this is basically what happened to it 6 months later. And this is only one of the examples of bridge incidents of the world. Basically, it was called Galloping Gertie because it was doing this for about 6 months. And people were trying to figure out why it's doing it. And by the time they figured out, this happened. And this is an example of a reliability problem. In that case, aerostatic flutter causing resonance and leading to this. That leads to a security problem and safety problem in your infrastructure over here. And this is the connection between reliability, hardware reliability over here, a bit flip that's causing a big security and safety incident. Now, people were lucky in this case because there were no fatalities, at least human in this case, but there are many other bridge incidents in the world where there were human fatalities, and we're going to get back to it if we have time. This is another example that I use again to motivate importance of reliable computing and secure computing to freshmen again. These folks are constructing Manhattan after the World War. They're very happy. But if they have a bit flip on this rod, maybe they're not going to be very happy very quickly, right? And again, I think this is very important because today our rods are really the computing infrastructures that we build. And if you really have bit flips, they're not reliable and they're not secure, all of these AI machines, whatever you would like to call them, then we're going to be in trouble because they're going to be making a lot of decisions. So I think of security as preventing unforeseen consequences. It's a very general definition of security, of course, but it's good to be general in this case than not so general because you don't know what you're missing, essentially. So if you can design these systems that can adapt to these unforeseen consequences in the field, then we can potentially prevent a lot of the incidents. Of course, I don't know how to do that, but okay. So DRAM scaling problem. Essentially, that's how I connect these incidents to the DRAM scaling. We've already talked about the DRAM scaling problem. Essentially, as you reduce the size of a DRAM cell, it becomes less reliable. And we've seen this picture, which is actually in the field. It's true. We're seeing more and more memory errors, and we haven't published some of these results yet. But I actually see in recent memories, the memory errors are increasing even more. Cells are too close to each other, but essentially they're not electrically isolated from each other, basically. And if you're interested, there's some old data in this work. And when we first started looking into DRAM scaling issues, we actually wanted to solve the refresh problem, retention time problem. How do you actually determine the retention times of a DRAM cell so that you can refresh the DRAM cells at the rate they need to be refreshed at? That actually gets rid of a lot of the refreshes, as we will see in a little bit. So we built these infrastructures to be able to test the retention times of DRAM cells. And later on, we actually wanted to test a bunch of other issues, like reliability issues, as well as latency issues. And I'm going to talk a lot about these FPGA-based infrastructures. And that has enabled us to discover some of the interesting error mechanisms also. And as I mentioned earlier, we've open sourced this infrastructure. I'm going to skip some of these slides that we already discussed. So one of the issues that we've studied immediately with this infrastructure, and the reason why we built this infrastructure, was to understand the data retention characteristics of different cells. And if you look at the retention time profile of DRAM, today we refresh every single cell every 64 milliseconds. Okay, in LPDDR, it's every 32 milliseconds. At high temperatures, it's every 16 milliseconds. And it's reducing. But if you look at this is yesterday, every 64 milliseconds was the standard. If you look at the retention time of real DRAM cells, it looks like this actually. Most of the cells don't require to be refreshed every 64 milliseconds. Most of the cells, you can reduce the refresh rate by 4x, and they still retain data perfectly. And now you've gotten rid of almost 75% of your refreshes. And that's the idea. So there's a lot of heterogeneity because of process manufacturing variation that you have. But these heterogeneous refresh rates are not exposed to the memory controller. The memory controller can potentially determine these, and that's exactly the direction that we pursued in our research. How do we actually figure out the retention times of these real DRAM cells by building intelligent memory controllers? So it looks nice over here, but it's not as nice. Clearly, this is location dependent. Different cells have different retention times. Actually, some cells have 100 seconds of retention times. People exploited that to launch cold boot attacks. You take someone's DRAM, put it into a freezer, for example, and then read out the data, and you can still recover a lot of the data. These are called cold boot attacks because DRAM is not losing its charge very quickly, at least not all of the DRAM cells. But the difficulty is this is also dependent on the value pattern that's stored in the cell and the cells around it because of electrical interference between the cells. And this is also dependent on time. There's a random process that we discussed, the variable retention time phenomenon. DRAM cells retention time changes randomly over time. So it's not easy to determine the retention time of a DRAM cell. And as a result, we built this infrastructure, and we actually built a lot of insight, at least for us and for others to use, to understand the retention time behavior. I'm not going to talk about a lot of these, but the takeaway is you really need intelligent memory controllers and some error correction capability to be able to exploit the fact that you have heterogeneous refresh rates. For example, this paper, we exploit error correction codes to figure out what should be the refresh rate of different DRAM cells. And these are the more recent papers. I'd be happy to talk about these separately, but I'm going to skip the refresh problem in this talk, sorry. But the takeaway is basically you need an intelligent controller to exploit this fact. But while we were doing these studies, we were actually very interested in looking at different other error types in DRAM. And we actually had a similar infrastructure in flash memory, FPGA-based infrastructure. I'm going to show you the pictures of later on. FPGA-based infrastructure where we could test the flash memory. And we knew from flash memory that there are a lot of read-disturb errors. Whenever you read a page, you disturb all of the other pages that are in the same block in flash memory. And this is a big problem in flash memory, actually. And we've designed mechanisms in flash memory to get rid of the problem. And we asked the question, do you actually have the same problem in DRAM? And it turns out the answer is yes. In flash memory, the problem is not as bad because flash is a controller that can fix all of those problems. In DRAM, if you have this problem, if you can predictably induce errors in a memory chip, and if you don't have enough error correction capability, then you have a problem because that error gets directly exposed to the programming language because DRAM is directly exposed to your programming language. Whenever you do a load or store, you're really accessing a DRAM, physical memory location. Okay, so that's the idea over here. That's the idea of RowHammer. Essentially, it's a simple hardware failure mechanism that can create a widespread system security vulnerability. I'm going to talk about the system security vulnerability too. And you've seen this already by now multiple times. So what's the problem? Essentially, it's a read-disturb mechanism. In DRAM, this read-disturb takes a specific form. In DRAM, you have a bunch of rows that look like this. And if you want to read data from a row, you need to activate that row, which means you need to apply high voltage to that word line. And if you want to read data from some other row, you need to pre-charge the array, which means that you need to apply low voltage to the word line from this word line's perspective. Now, if you keep doing this repeatedly, activate, pre-charge, activate, pre-charge, activate, pre-charge, activate, pre-charge, activate, pre-charge, enough times before the cells get refreshed, it turns out some bits, some vulnerable bits in adjacent rows get flipped from 1 to 0, 0 to 1, depending on the coding. There's analysis in the paper that talks about this also. But they get flipped. Essentially, you lose the data value in them because you're able to do these activations enough times that disturb the values over here before the cells get refreshed. And why is this happening? Because cells are too close to each other. They're not electrically isolated from each other. As a result, when you're opening this word line, one of the error mechanisms is this. When you're applying high voltage to this word line is also getting some of that voltage. So you're applying that voltage to that word line. It's partially opened. As a result, some vulnerable cells are leaking charge a little bit into their bit lines, and they're losing that charge. And if you do this enough times before they get refreshed, some of them lose enough charge that you cannot recover the data value that was there. That's the idea. So it's really an electrical isolation problem. We call this the hammered row, and we call these the victim rows. And we've essentially shown that in most DRAM memory chips that we've tested at that time, which is representative of the DRAM chips that you could buy at the time, are vulnerable. So what is most? Most is more than 80% of the chips that we've tested. And this is across 3 major manufacturers, ABC. You can probably guess what ABC is, but not exactly the exact mapping of the names of the manufacturers to ABC. But this is an industry-wide problem. Basically, it's not a specific manufacturer problem. And it's a scaling problem because this didn't appear in chips that were manufactured before 2010. The chips that we've tested that were manufactured before 2010, they were fine. But the first appears in 2010. And all of the chips that we tested that were manufactured between 2012 and 2013 were vulnerable. It didn't depend on the manufacturer. It really depended on some things in the chip. You can see that the error rates of the manufacturers are similar. It depends on the technology also, but essentially it's a scaling problem. So clearly, read disturb is a very fundamental phenomenon in any memory. You'll find it in SRAM, DRAM, flash memory, hard disks. Clearly, read disturb was happening before, but because cells got too close to each other over here, now you were able to, the number of activates you could squeeze in a refresh interval in 2010 were enough to cause these adjacent cells to flip, essentially. So read disturb was still happening before, except it was not getting visible as bit flips until 2010. Okay, so this is a scaling problem, as we see. I think I already discussed this. DRAM cells are too close to each other, and I'm not going to talk about this. This is a copy-paste from my freshman lecture, by the way. So higher level implications. This actually has higher level implications. You may say that this is simple circuit level failure mechanisms, but it gets exposed to the programming language, and as a result, it affects the user. So when we wrote the paper, we actually released this code also, and this code is also in the paper. Basically, it's a user-level assembly program that can induce these bit flips. It selects address X and Y. Probably it doesn't work right now because it works on specific computers. You need to really reverse engineer the bank mappings that you have in DRAM to be able to do this. You might be better off taking some of the code that was developed by security researchers that was released right now. Essentially, you can think of this code as taking address X and Y in the same bank and bypassing the caches, bypassing the row buffer in DRAM, and essentially doing this. Ping-ponging activates to X and Y. And if the chip is vulnerable, you'll get errors. That's the idea. And it's a very simple user-level code. You don't need any kernel privileges to be able to do this. You can download the code. Better yet, you can download code from Google Project Zero, who later turned this into a security attack. So one of the things that we realized in the paper was if you actually hammer a particular row, if you select X and Y such that there's only one row between them, you actually get a lot more errors. So we didn't release it in this program, but Google took this insight and they basically showed that, they call this double-sided hammering, and they showed that you could actually induce bit flips even faster with the fewer number of, even faster by sandwiching a victim row in between two hammered rows. And that's why their code is more powerful. And we showed in the paper that you can actually get errors in Intel and AMD devices. There's nothing special about Intel and AMD. As long as you have a memory controller that can do these activates enough times within a refresh interval, you get these errors. Later, people have shown that all of the processor manufacturers are vulnerable because we are able to design these controllers to do enough activates. There's no question about that. Yes?
Why is the 1 order of magnitude difference?
Why is this so small, you're saying? Yeah. Well, actually, we don't exactly know, but clearly, for some reason, this particular generation of AMD pile driver was not able to access memory fast enough. As a result, it was able to induce errors that are small. And error rates are not really linear with the access rate. It's a different curve, basically. That's the reason. But later AMD devices actually don't have this problem. It so happened that the device that we had was not able to have a higher access rate. Okay, that's a good question though. Okay, so this is actually a reliability problem because real applications may be able to do this. In fact, we have some evidence in the field that some real applications cause this problem. And when you get a bit flip in a real application because of this, it's a nightmare to debug. There was a presentation from Google in 2014 in DSN where they talked about, this was a keynote presentation, this was a software engineer presenting this, and he said that their team spent 8 months to chase a hardware bit flip. It was not a RowHammer bit flip in this case, but the RowHammer bit flips actually can happen also in real systems. But it's more of a security problem actually. When we first wrote the paper, we said that memory isolation is a key property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on data stored in other addresses. I still believe this. I think it's very fundamental. And we said that you could actually design a security attack that could hijack your system. And while we were working on it, the good folks at Google Project Zero, Mark Seaborn and Thomas Dulien, they basically showed exactly that. They published a blog post where they showed that with a user level mechanism you could gain kernel privileges. And I'm copying and pasting directly sentences from their blog post over here, but if you're really interested, you should take a look at the blog post. It's beautiful security engineering. They basically said they learned about the problem from our work. They replicated the problem in their systems, and they built 2 working privilege escalation exploits. One of them is not that interesting to me. It takes over the Google native client, which is actually an attack that's similar to an attack that was published in the security community in 2003, IEEE Security Privacy. There was a paper by Andrew Appel's group that basically, it's called Using Memory Errors to Attack a Virtual Machine. And they had the same idea actually. The idea is, if you can induce memory errors in a machine, you could take over the virtual machine. All of the sandbox provided by the Java virtual machine you could overcome. Now the way they induced memory errors in that machine was they had physical access, and they actually put a lighting source, temperature source to the memory, and they induced a lot of bit flips. So they didn't have controlled error injection. What RowHammer enabled is to have a programmatic mechanism where you could actually induce those bit flips in a very predictable way through the software without having any physical access, clearly. And these folks exploited the fact that to actually gain kernel privileges in x86 Linux. I think this is the more interesting attack that they developed. With a user level process, they were able to gain access, induce bit flips in the page table entries of the process that points to its own page table. And if you actually flip the right bits in your own page table, you can gain write access to your own page table. And once you gain write access to your own page table, you actually can change all of the permissions that you have to the entire physical memory, entire virtual memory actually. And as a result, that you can take over the machine. So that's the idea. Of course, this is simplification, right? You should take a look at how they actually did it. It's not an easy attack. It's a probabilistic attack, but they were able to do it. And people start drawing pictures like this. This is the RowHammer. And I like this analogy over here by a famous hacker. Basically, he said that it's like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door that you were really after. It's really a vibration problem that you're exploiting over here. I'm going to go through some security works very quickly over here. I'm not going to focus on a lot of them in detail, but I think this is fascinating because this single bit flip, RowHammer, enabled a lot of research in security. It's also actually very interesting from a different perspective because people knew that these bit flips can be exploitable. This IEEE Security and Privacy paper from 2003, I think it's a very nice paper actually, I would recommend reading it, showed that exactly. But there was no research that did anything until people figured out that, okay, RowHammer enables these bit flips in a real system. So it's an interesting mindset. Once you have these bit flips in a real system, the entire security community can actually do research. Until then, even though you know that bit flips can be exploited to take over a machine, you don't do anything. I think this is a bit different from architecture, where we're very used to doing stuff that doesn't exist, right? Whereas in security, it's a bit different. Okay, anyway, I'll go through this relatively quickly. As I said, double-sided RowHammer. There's actually some other work that looked at CL flush-free RowHammer. I'll go through this relatively quickly, but this is just more for a reference over here. There's a bunch of work, and this is not comprehensive. I'm going to point out a couple of them later on with pictures. But I'll point out something really interesting, for me at least. Okay, this is a lot. Okay, this one is interesting. Actually, the first folks who picked up on our work was actually the MemTest software work, this passmark software in 2014. Quickly after reading our paper, they actually introduced a test called RowHammer test. And apparently they got a lot of reports from people saying that, oh, we're actually seeing a lot of errors with this test. So if you read their website, why am I only getting errors during test 13 hammer test? So they're not getting errors in any other tests in memory. Memory is very reliable otherwise, but when you hammer it, it becomes unreliable. The errors detected, so they had to say on their website that the errors detected during test 13, albeit exposed only in extreme memory access cases, which is hammering, are most certainly real errors. So they had to assure people that they're real errors. I find this fascinating. And they actually talked about some of the interesting things. So this is interesting to look at. And this is from our presentation actually. We said that you could develop disturbance attacks. These folks from TU Graz, some of them were actually later involved in Meltdown and Spectre. They showed in 2016 that they could induce these bit flips in remote machines through JavaScript, and they could take over access to systems of website visitors. It's a very interesting attack, I think. This is one of my favorites also. These folks are from Vrije University in Amsterdam, who've been doing a lot of work on RowHammer, but one of the works they did was they showed that you could do this on an Android phone in an ARM-based system. A lot of people, for some reason, I don't know why, believe that you couldn't do this on ARM-based systems. It doesn't make sense to me, but they showed that you could do this on ARM-based systems. That's one. But I think the more interesting part of what they've done is they were able to take over the system deterministically, meaning that they showed that the Android memory allocator had deterministic memory allocation patterns. They profiled memory on a phone. They actually have an app you can download and see if your phone is vulnerable, or you can get hacked by their app if you want. I'm sure they're going to be the white hat guys, not the... Anyway, basically they showed that you could profile memory, figure out parts that are vulnerable to RowHammer, and then you could fool the operating system to allocate a page table entry in a page that's vulnerable to RowHammer. And then you would hammer that page by hammering the adjacent location and induce bit flips in that page, and then you could gain access. Basically, you could essentially gain privileged access to that particular cell phone. And you could do this deterministically because you know how the memory allocator allocates in the Android operating system. This is again beautiful piece of security engineering, which is again enabled by the fact that RowHammer exists in real systems. Okay, and then these folks started doing a lot of interesting attacks. They showed that you could do these attacks much faster through GPUs, because GPUs have very high access rates to memory. They could activate much faster, and you could do this again through the WebGL interface in a mobile system. You could do these attacks through the remote direct memory access interface that you could have to a remote server. That's actually very interesting. And actually two groups published papers at the same time. This is another paper that did the same thing. And this is a more recent paper that is going to be published in the Security and Privacy, Top Security and Privacy Conference of IEEE, where you could actually leak data using RowHammer, which is also interesting. Well, you can read the paper, it's already out. And then other people looked at other things that I'm not going to talk about. And this may be another attack that you have on your computer if your computer is prone to bit flips. Or maybe there's a solution, I don't know. Again, there's a joke, of course, right? Okay, so let me talk about understanding RowHammer a little bit, and then we're going to talk about solutions, and then I think we're going to take a break after that. So we wanted to understand RowHammer at a very physical level. It's not easy to do. You cannot replicate the problem with circuit level simulations. That's why we actually did a lot of device level studies. But these were some root causes that we verified with at least one manufacturer. It's two right now. Manufacturers were very reluctant to talk about this initially. Now they're actually talking about it, which is nice, which is good. I mean, they have to talk about it. It's real, right? basically, one of the causes is electromagnetic coupling. Conductor bridges get formed actually across different rows. Hot carrier injection is another effect that affects us. It causes permanent faults. We haven't seen it as much, but we believe that it plays a role in RowHammer also. And the causes are really entangled with each other. And the causes are becoming worse as you reduce the size of a cell. So the RowHammer at a physical level is actually becoming worse. The number of activates that you have to do to cause these bit flips are becoming worse in devices today. Now this doesn't mean that they're going to be exposed to the systems, of course, right? Clearly people are going to design solutions. So we're going to talk about solutions. So with our infrastructure, we did a lot of studies. I'm going to show you a couple of examples over here. We tested, this is our initial paper, we tested a bunch of 129 modules at that time, and we showed a bunch of results. One is, what is the address difference from the perspective of the memory controller between the hammered row and the victim row? It turns out the addresses are mostly logically adjacent. These are logical addresses. But some of them are not adjacent. You see that there is a row address difference of 3, sometimes 7. Meaning that they're not logically adjacent. This doesn't mean that they're not physically adjacent. Because what happens internally is some row addresses get remapped internally by the DRAM manufacturers using a function that is not exposed to anyone else in the world. And you may actually get some logically non-adjacent addresses mapping to physically adjacent addresses. That's our explanation of this. Of course, we cannot perfectly verify, but the takeaway is most of them are logically adjacent. There are some cases where they're not adjacent. Okay, so this may help with some solutions, but not all of the solutions, of course. But we are going to get back to this. This means that the memory controller doesn't know perfectly which rows are adjacent to each other. So if you want to implement a memory controller-based solution, you need to expose this information to the memory controller. I believe this information needs to be exposed to the memory controller for many reasons, for a lot of benefits, but this is one example where this information should be exposed to the memory controller. Okay, the other takeaway, this is the access interval. Basically, how frequently you can activate an aggressor or a hammered row. Basically 55 nanoseconds, below 52.5 nanoseconds was not allowed in the chips we've tested. So of course, clearly if you increase the access interval, you should get fewer errors. This is error rate over here, and this is the access interval, and that's exactly what we see. Meaning that one solution could be throttling accesses to an aggressive access pattern. Now a very naive solution could say you never access a row, you never activate the same row until 500 nanoseconds passes before the after the previous activation. Now this is a terrible solution, of course, right? Whenever you get a bank conflict, for whatever reason, you wait for 500 nanoseconds from the previous activation. I don't think this is a very good solution. Maybe selectively done, this could be a solution. But we showed that if you employ that solution, you need to wait for 500 nanoseconds in the worst case. Okay, so this is actually important because this affects the real systems. In real systems, you can have a lever, you can play with the refresh rate, and you can fix the RowHammer errors by increasing the refresh rate. So this is refresh interval. As you go to the left, you increase the refresh rate, and this is the error rate. Clearly, as you increase the refresh rate, meaning reduce the refresh interval, make more frequent refreshes, you should get fewer errors. Because you should be able to sneak in fewer activates within a smaller number of milliseconds, clearly, and that's exactly what we see. Now the good news is you can solve a lot of the RowHammer errors by increasing your refresh rate. The bad news is if you want to get rid of all of the errors just by increasing your refresh rate, you need to increase your refresh rate a lot. 7x according to our experiments. And these are the worst devices that we've tested from manufacturers ABC, and they're reasonably close to each other. As you can see, you could 4x, 7x, they're around that area. But it's definitely more than 2x, as you can see over here. Okay, so more frequent refreshes lead to fewer errors, and that could be one solution. And that's going to be a good solution in the field, in my opinion, because we don't have any other choice. So data pattern is also important. Wait. Yes, please.
Comment. I mean, the power is going to be huge.
Yes, absolutely. I'm not condoning. I'm not saying that you should use the solution in future devices, but if that's your only choice, either you're not secure or you waste power, right? Yes.
Can you go back one slide?
Sure. This one?
Yes.
Yeah.
Because before you said you couldn't attack one row faster than like 50 milliseconds. Shouldn't that mean that the error shouldn't decrease when you make a refresh rate lower than like 50 milliseconds? Because that would mean for every access you make one refresh. And here you make even more refreshes for one axis.
So
30 seconds. Okay, sorry.
Yeah, this is okay. Okay, good. yeah, there's a 3 order. Is it 3 orders of magnitude? That's 6 orders of magnitude, right? Yeah, yeah, that's the difference. Yes.
How many times do you have to hammer a row?
So that's a great question. In the paper, we show that you need to do it, let's say, 100K times. But again, this is Google later improved it. You could do it with 50K. I believe going forward, it's going to reduce actually.
Go back. The 500. If you do a rate restriction, it should be 500 nanoseconds for a bunch of axes, not for one.
That's right, exactly. So basically, you wait 500 nanoseconds between these different axes so that you're hammer prone. You fix the hammer. Yeah.
So it may not be tragic.
It may not be what?
Tragic.
Yeah. Yeah, I mean, you can look into a lot of data. These are data from real devices, by the way. It's all based on testing of real DRAM chips. Okay. So data pattern also matters. Actually, this determines how vulnerable some of the cells are to errors because of electromagnetic coupling again, because coupling capacitance is much higher in this case, whereas it's not as high in this case. And we found out that you get 10x, an order of magnitude more errors if your data pattern looks like this and then you do the hammering that way. And that's true for refresh also actually, retention times also. You have much worse retention times in this data pattern compared to this data pattern, for example.
It should be also very different from vendor to vendor.
Yes, absolutely. So there is certainly a vendor dependence over here. But data pattern still, so the worst case data pattern is different from vendor to vendor, but all of the vendors are affected by the data pattern dependence. Because this really depends on how the coupling happens, and all vendors have different types of designs inside their DRAMs. Exactly, yeah. Okay. So there are a bunch of other results in the paper, which is really I think this is very interesting. Basically, RowHammer is a completely different failure mechanism than retention loss. And we actually proved that in real device, experimentally, empirically proved that, of course. We don't theoretically prove it. But there's almost no overlap between these cells that are weak because of retention time versus that are hammerable. Errors are not strongly affected by temperature. Again, this shows that retention time is a very different process, failure process, compared to RowHammer. And errors are repeatable, and this causes the security problems, actually. If you're able to induce a bit flip in a bit, you're going to be able to do it again and again and again, which means that you can profile the memory, figure out which parts are vulnerable, and you can use that fact later on at some point in time. We found out that a simple ECC cannot prevent these errors, and I think this was obvious to us, but recently some security folks showed that you could reverse engineer the ECC mechanisms that you have in memory controllers, and you could actually devise an attack that would take advantage of RowHammer to take over a system, even on a system that is protected by ECC. Because of this fact, basically, because ECC is not enough, essentially. At least simple ECC is not enough. Of course, you may have very sophisticated ECC that can prevent a lot of errors. That's one solution to the problem. I would argue that that's a bad solution to this particular problem, because ECC error correcting codes are very good at fixing errors that are random, whose causes you don't know, but they're very inefficient at fixing errors that otherwise that you could fix easily. I believe RowHammer errors are fixable easily with other mechanisms. ECC is a very big hammer that causes a lot of inefficiency to fix the errors. I say this because I think this is obvious right now, but DRAM manufacturers were sometimes not so. I don't know what to call it, but I gave this presentation at ISC. It was an invited talk. ISC is, you know this one, right, Matthias? It's International Supercomputing Conference that happens in Germany all the time. And my talk was, I talked about RowHammer and also in-memory computation. And the next talk was from Micron, and they started the talk, and this is a very good guy actually, but he started the talk by saying that I have a solution for RowHammer. It's 3 words, not three characters. And he said, ECC. I don't think that's true, actually, since that's not the way DRAM manufacturers are solving the problem also. But I think it's good the security community is actually showing that you could induce these attacks on real ECC protected memory. So I definitely encourage the security folks to do more attacks to hardware so that we can actually have much more reliable hardware going into the future. Because sometimes I think companies need more motivation to make their hardware better. By the way, I work with DRAM manufacturers also, so it's good to have a good perspective, though. Okay, this is actually interesting. I think number of cells and rows affected by the aggressor is different. It's not just the adjacent row. We found out that non-adjacent rows get affected also, but it actually drops exponentially. But I think going forward, this is going to become a bigger issue, which I'm not going to talk about right now. This is the observation that led to this double-sided row hammering by Google and other folks also. Well, Google was the first. Basically show that cells are affected by two aggressors on either side, and you can actually have double-sided row hammering because of this. And if you want more, this is the original paper that talks about it. I wrote a slightly different paper in date in 2017, and we were invited to write this paper more recently, which appeared in June 2019, I think, in TCAD. And we did a lot of research into this article, actually, looking into a lot of the RowHammer work that appeared afterwards, and talks about a lot of different types of RowHammer work. If you're really interested in this topic, this may be the reference, but be advised that this doesn't include, for example, the RAMBleed paper that I mentioned. So there's work that's going on in the field. This may be a checkpoint in maybe April 2019. Okay, now let's talk about solutions. I think I've talked about some of the solutions, and there was some conversation about it also. So I think there are two types of solutions that we need in any type of vulnerability like this. Immediate, meaning that we need to protect the vulnerable DRAM chips in the field, but we have limited possibilities for that. But the longer term solutions can be more creative and hopefully more well thought going into the future to protect future DRAM chips. And hopefully the solution is not ECC. Because we want ECC. We want to reserve ECC for really those errors that we don't know the causes for. Like variable retention time is a perfect example where we can use the ECC because those errors are random across the chip and across time also. So, but we can have a wider range of protection mechanisms over here. We talked about both types of solutions in the paper. There are 7 solutions. I'm going to cover some of them, but I'm going to focus on a couple of them. So I think Para is one example that's already somewhat employed in the field. At least the basic principles are employed. But I think we need to do more to get the principle. So these are some potential solutions. I think making better DRAM chips, good luck with that. Like this could have better materials that provide better electrical isolation. I think it's not very easy. Refreshing frequently, we're going to get back to that. Sophisticated ECC, I said sophisticated over here, not simple. Access counters. Clearly they have a lot of issues related to this. I think access counters need to be exploited more. What I mean by access counters, somehow figuring out which rows are being hammered. We were a little bit pessimistic about the solution in our paper because we said that this will cause a lot of hardware overheads. And I still believe that this can cause a lot of hardware overheads, but maybe there are mechanisms that you can develop that can make it less costly. And there are some works that are appearing that are less costly. Still, their cost is a bit high in my opinion, but there's more research that needs to be done in this area. So throttling access to the same row, if you couple it with the access counters, I think this could be a good solution potentially. Refreshing more frequently. Again, if you really want to do this perfectly, you may actually run into a lot of overheads. So what is the solution that's employed in the field today? Basically, we're refreshing more frequently. This is Apple's patch. I like Apple because they actually clearly say they're increasing the refresh rates to solve the problem in a security vulnerability, actually. You can read it over here. They basically said RowHammer exists, and at least the memory corruption, this issue was mitigated by increasing the memory refresh rates. And they were nice enough to credit us also academic work. I think it's good for companies to credit the academic work. And essentially all manufacturers employ the same solution. They don't tell exactly how much they increase the memory refresh rate. Probably it's 2x, that's my guess. Probably it's not 4x, but it's not a good solution clearly. But this is the only easy solution that you can employ because you have that level of program built in your memory controller. Of course, this requires a software patch to change it, right? So our solution was probabilistic. Essentially, the idea is very simple. After you close a row, you activate one or both of your neighbors with very low probability. And you set your probability based on your comfort level. And if you set your probability nicely, you get a reliability guarantee that's much better than many of your other components in your system. And if you're paranoid, you can increase that probability, of course, right? And the good thing about the solution is its overhead is very low because you're not increasing the refresh rate across the board. You're sneaking in 1 or 2 refreshes to adjacent rows once in a while with very low probability. And as a result, our results show that it doesn't have a lot of overhead. It also doesn't need to track any state. If you want to keep track of which rows are being accessed a lot, which rows are being hammered, you need to keep track of some state. In this case, we don't need to keep track of state because it's probabilistic. You just want to do it. You can do it deterministic also, actually. It doesn't need to be randomly determined, but it's low cost and low complexity. It only needs 2 counters to be able to do this. So it's essentially an effective and low overhead solution. But of course, its implementation requires a challenge. You could do this in a DRAM chip or in the memory controller, and they both pose different challenges. If you want to do this in a DRAM chip, how do you do it? Essentially, you exploit the slack and timing parameters. In DRAM chips today, you wait for a longer amount of time after you pre-charge than you really should, because there's a lot of timing slack. During that timing slack, maybe there's enough slack to sneak in another refresh to adjacent rows. And this is actually done by DRAM manufacturers in a similar way, not exactly in the way I described, but they exploit the slack in the refresh cycles, for example, to sneak in more refreshes for rows that need protection. Does it work in all cases? I'm not sure. I think this requires more testing, clearly, and I think security researchers have a big role to play over here to keep hardware more secure. But I don't think this is a good solution, actually, in the long run, in a principled approach, because actually slack in timing parameters is not good for latency. We want to get rid of slack to reduce the latencies, and I believe in reducing latencies. And if you get rid of slack, then you're not. Essentially, this is a hack, in my opinion. You have the slack for some other reason, and you're using it to correct an error that you could otherwise correct in some other way. Okay, but this is a potential solution, and we've seen that there's a lot of slack, and we actually are going to talk about, hopefully, if we talk about latency, that we can get rid of a lot of that slack to reduce latencies in DRAM significantly, like 30 to 50%. I believe a better, more principled solution is to actually do this in the memory controller, similar to the proposal that Intel and Samsung had, saying more intelligent memory controllers overcome these scaling issues. But of course, this requires more information to the memory controller. Memory controller now needs to know which rows are adjacent, physically adjacent to each other. And if you don't have this information, how do you do it? In a reliable manner is difficult. Now, the interesting thing is, Intel has a memory controller that did this. You could buy this very recent Intel chip. Basically, you could pick your RowHammer solution. It could be hardware RowHammer protection or 2x refresh. If you pick hardware RowHammer protection, you could pick a different activation probability. Now, you could pick a RowHammer induced refresh every 2 to the 11 activations, for example, every 512. Or you could do it every other activation. Probably not a good idea. It's not exactly how we envisioned it, and there's not enough detail on this, actually. I talked to some Intel memory controller folks, but I cannot disclose a lot of information about that. But it exists, at least. Yes?
So they just send them activated pre-charge commands?
So that's what I believe they do, yes. Exactly. And they do it probabilistically, very similar to para, except they don't know which rows are adjacent, so they have to guess which rows are adjacent. And that's where the information stops. So it's not clear if this prevents all errors, but I guess if you do it, yeah, it's not clear, basically. I shouldn't say anything more than that. But I think it's a step in the right direction because it's putting intelligence in the memory controller to solve these problems. Okay, I think I've talked about this a lot. I think I'll talk about this again. Main memory needs intelligent controllers for security purposes also. So imagine if we had a more intelligent memory controller that we could program somehow. If we had a patchable memory controller that we could change in the field, maybe we could solve the RowHammer problem much more easily. Again, I don't know how to build that controller exactly. I can imagine some cases, but if we had that, we wouldn't need to increase the refresh rate significantly. So as a result, people are writing papers about this too. They didn't talk about RowHammer clearly in this work because RowHammer was introduced in the same conference where this work was published, actually. But I think they had something important in mind when they said that we should really design more intelligent memory controllers to fix the process scaling issues that we have with DRAM. And we know how to design these intelligent memory controllers. I promised that I would show you our flash infrastructure. This is our FPGA-based flash controller, where we did a lot of studies in terms of the error rates and different types of errors in both 2D and 3D flash. And if you're interested, I'd be happy to talk about it. I'm going to point you to a paper. I'm not going to talk about flash as much in this tutorial. But basically, flash controllers are very intelligent. They actually do a lot of different types of things. They do very intelligent voltage optimization, read disturb optimization. They do things like neighbor-assisted correction of different rows or pages, which was proposed in one of these papers over here, in the Sigmetrics paper actually. So they can do this. We can design these controllers, except flash has a lot of slack actually, because the latencies to flash is very large. I think we just need to do this in DRAM also. Maybe design a DRAM translation layer where DRAM is more like flash, but we need to do it very, very fast. And this is the paper that they've written recently about a lot of the work. It's a survey of how flash controllers work in terms of characterizing, mitigating, and recovering from errors that they have. And you can see that there's a lot that goes into this infrastructure. And this has actually enabled flash to be very, very good in systems. So I think main memory also needs these intelligent controllers. So let me quickly talk about some future challenges, and then we're going to take a break. So future of main memory, I think, is a bit bleak. Basically, DRAM is becoming less reliable and more vulnerable, and I've already given you examples of this. And flash is also becoming more vulnerable. We've actually done a similar study with Facebook where we showed that flash is becoming worse. And due to difficulties in DRAM scaling, other problems may also appear, or they may also be going unnoticed. Some errors may already be slipping into the field. I think these are there to be found, and I hope people will find them. Read disturb errors are an example, clearly. RowHammer retention errors could be slipping into the field. These may be a bit harder to find. Read errors, write errors, they may be slipping into the field, and who knows what. As a result, DRAM manufacturers are putting error correcting codes inside the DRAM chips right now. If you went to a DRAM manufacturer 10 years ago and said, I want error correcting codes in your DRAM chips so that I can have more reliability, they would kick you out of the room. Because this cuts directly into their costs, right? Because they have to reserve some amount of the chip for error correction, and that reduces their capacity that they can sell. Essentially their cost. But now they're putting it so that they can prevent these scaling issues that they cannot prevent in other ways. But maybe error correcting codes are not enough to prevent them also. As a result, slipping errors can pose security vulnerabilities. By the way, the error correcting codes chips, LPDDR chips, are all error corrected, protected with error correcting codes right now. And I think going forward, all of the chips will be. Okay, I'm not going to talk about retention errors. If we had more time, I'd be happy to talk about retention errors. But I'm going to talk about, very quickly, the fact that determining the data retention time of a cell in row is getting more difficult. Okay, there are backup slides on this. We don't have enough time, and I want to talk about other things. When did we need to take a break? Okay, now, let me finish this and then we're going to take a break. I think we're almost done. So basically, there are also emerging technologies that suffer from similar issues, actually. So the key question is, how do we fundamentally design memory and computing architectures in general to be secure, reliable, and safe? I believe we need to somehow predict and prevent these safety. I use security, safety, and reliability the same, because RowHammer actually affects all of them. They're not the same things, clearly, but I think with bit flips, in my opinion, they affect everything. But somehow we need to predict and prevent them. The question is, how do we do that? This is my recipe that we're following to be able to do that. I think we need to be able to understand first. We want methods for vulnerability modeling and discovery. We want to somehow model and predict based on real device data analysis and understand the vulnerabilities and develop reliable metrics. I don't know how to do the metrics part, especially for security. We need to have principled architecture with security as key concern. Somehow we need to partition the duties across the stack. Memory controller memory, even that we didn't get right so far. I believe with research we'll get it right. We cannot give up performance and efficiency, clearly, and I believe patchability in the field is really, really important for components. And I think design and test has a lot to play over here. Like, we need to principle design, automation, and online testing techniques that actually take security into account from the very beginning. And of course this needs to play well with the other system reliability methods. So that's why we've been building these infrastructures so that we can understand and model. And also Flash, actually, there are a lot of models that we developed for Flash. So let's recall this picture that I showed you earlier. This is the galloping Gertie, right? I think in systems like this, we don't have a lot of patchability. But in computing, We have a lot more freedom, actually. We don't need to build computers like bridges, because bridges are very hard to patch in real life. As a result, we had much worse incidents. Some of you may remember this. This is on Han River in Seoul. This is in Minneapolis. These are all actually deadly incidents. And this is in Genoa in 2018. Maybe there's a more recent one that I don't know of. But I don't think we have patchability in bridges, but I think in memory we can have a lot of patchability to prevent these failures. Okay, let me give you some final thoughts on RowHammer. I think it's really interesting, giving you some stories. But how to exploit and fix the vulnerability requires a strong understanding across the transformation layers, I think. I already discussed this, but this is actually a slide that I borrow from Satya at CMU. He teaches the system course, and he talks about Byzantine failures a lot, and he gives RowHammer as a real example of a Byzantine failure. Essentially, Byzantine failures are characterized by undetected erroneous computation, and RowHammer could lead to this. Essentially, this is opposite of fail fast. Ideally, you would like to fail fast, right, with an error or no result. But with RowHammer, you get a bit flip, and as a result, you don't know who's actually plotting against you. And errors, erroneous, can always be malicious. The only distinction is really the intent, right? You may get an error that's benign. You may get an error that could be exploited for malice. And it's very difficult to detect and confine these Byzantine failures. So we really need to do all we can to avoid these things. And especially with machine learning relying on hardware a lot more going into the future, we really need to do this. And if you're really interested in the Byzantine failures, this is the seminal paper that introduced the problem. Okay. So let me, in the retrospective, I think from a retrospective perspective, RowHammer enabled a new mindset that enabled a renewed interest in hardware security research, because real memory chips are vulnerable in a very simple and widespread manner. This caused real security problems. So hardware reliability and security connections are now mainstream discourse in the security community. There are many new RowHammer attacks. I've given you some examples. There are tens of papers. Even in 2020 right now, there are some papers. I believe there are more to come. RowHammer is getting worse at a device level, but the attacks will be difficult to find out in DDR4, DDR5, because people will be adding protections. The question is, will you be able to figure out attacks, I guess. There are many new RowHammer solutions. I think there should be even more RowHammer solutions going into the future. I've given you some examples over here. And I believe the good solutions require principled system DRAM co-design. And I believe there are more to come over here also. I think the mindset is also more important. I mentioned this, right? These bit flips were well known, but nobody exploited them until RowHammer. The good thing is that people have this mindset that hardware is vulnerable. General purpose hardware is fallible in a very widespread manner. And I think this is very good for hardware security research, because the really interesting things that are happening in security are in hardware right now. That mindset has enabled many systems security research to examine hardware in more depth and understand hardware's inner workings and vulnerabilities. And I think it's really good that people have done that, and people should more of that, because the people who worked on RowHammer originally, two of the groups went on actually and discovered Meltdown and Spectre later on. And I believe there's more to come in this one as well, in hardware security issues. Okay, so let me summarize. DRAM reliability is reducing. The reliability issues open up new security vulnerabilities as well. And these are very hard to defend against in the field if you don't have patchability in the field. RowHammer is the prime example. Its implications on system security research are tremendous and exciting. So the bad news is it's getting worse. The good news is people are providing solutions, but there's even more good news. As researchers, we have a lot more to do, right? We have these real failures that we can discover and also fix. We're now fully aware that hardware is easily fallible. And we're developing both attacks and solutions. And hopefully we're developing principled models, methodologies, and solutions. And again, if you're really interested, you can take a look at this paper that covers 5 years of RowHammer research. And I'll end the second part with this one. Any questions? Yes, please.
I have the first question. So when you talk about RowHammer attacks, is it always attacking rows to attack closed rows, or are there several flavors of RowHammer attacks? Can we imagine other ways of attacking?
Yeah, so essentially it's all of the attacks that I've seen are to physically adjacent rows. Now I think there is a weaker effect on the next adjacent row and then the next adjacent row, but I have at least there's no evidence that people are exploiting those types of errors. So
the main source of it is basically that basically the access transistor and the cells, or two cells, are sharing parts of the same access transistor.
Yeah.
And this is where this path comes. So it's mostly only likely that you can flip really adjacent things.
Yeah. Well, it's not true actually. We found that non-adjacent rows get affected too, because there are multiple reasons for it. It's not just the access transistor sharing; it's really the capacitance coupling as well that happens across the word lines.
So imagine that these parts come from this redundancy remapping.
Well, that's one of the reasons. Yes. Yeah, exactly. That's one of the reasons. But really, there's a weaker effect, and we've seen this in Flash also. It's not specific to DRAM. So if you look at Flash, read disturb also exists in Flash. Whenever you read a page, you actually affect the pages that are across you. But we've seen we're actually able to quantify it much better in Flash, because you know the voltages of everything in Flash. We found out that when you disturb, the adjacent cell, immediately adjacent cell, gets the highest effect. The next one gets an exponentially decreasing effect. So you can disturb the next one also. And it's a very similar mechanism, I think, but it's a much weaker effect. That's why people have not exploited that as far as I know. But I think it's going to get worse into the future, because things are getting too packed. And we've seen this in Flash that's really packed together. And we actually have the exact numbers. I can point you to the paper saying that I believe 78% of the interference voltage change comes from this particular, affects this next cell, and maybe 9% affects the next one after that. So we have this equation that you can construct in terms of which cells are affecting you. Yes?
Are you aware of any efforts that deal with this by feature isolation at semiconductor level?
So that's a great question. Basically, people are looking, as far as I know, people have been looking at isolating materials. The problem is it's more costly. DRAM is very optimized with the materials that we build today. Any kind of isolating materials changes the process, and also it's just costly.
And the easiest solution would be one access transistor per DRAM cell.
Yeah, but that's, again, it's cost.
It costs,
Exactly.
Just introduce that to basically use more or less one transistor for two cells, basically. Or it's not really one, it's
Sharing the drain, basically.
Yeah, they are sharing the drain.
So
that was a decision. So if you see where the capacitors are placed, because they are really big, they are huge, they are going up, and they have to place it in a way, and this was an efficient method to use basically a shared transistor for two devices.
Yeah, of course, if you get rid of that, then your area increases, right? So that's also a cost. It's not clear if that will solve the entire problem, because there are other effects that also happen. So I think there are a bunch of efforts, but it's everything comes at a significant enough cost at this point at the device level.
Thanks.
Sure. Anything else? Maybe it's time for coffee then. Yes. Okay.